Okay, thank you. So today I'm going to talk a little bit about biofabricated materials specifically, but I'll first of all delve into a bit of background as to why certain areas of it are most important to me and my work. So I'll just start with how we are facing a triple planetary crisis of climate change, biodiversity loss, and pollution. And unsustainable patterns of consumption and production have been identified as the common thread of this triple crisis. So this is a good area really to be targeting when we're trying to resolve several of these problems that we have. And that's not too surprising when you look at the figures, which are that resource extraction and processing account for over half of our greenhouse gas emissions, most of our biodiversity loss and water stress, and a huge proportion of our particulate matter pollution as well. So taking a step back from that, what resources are we depleting? What are we extracting from the earth continuously and ending up in landfill? Well, all of our extraction overall has been going up steadily since the 1970s, but this graph here shows just the proportion of how this is separated per type of material. So you'll see here that the non-metallic materials are coming in at over almost half of our extracted materials. And this would include items like sand, gravel, and clay, which are largely used for the construction industry as well as other industrial processes. And then we have coming in second bio-based materials. So we'd have things like the food chain, agricultural uses, as well as timber and fish. And then the remaining parts are metal and also fossil fuel extraction. So then when we look at what we're using all of these materials for, well, the greatest consumer is, of course, the construction industry by far. And this is followed by food and feed and agriculture again, and it's split into several other areas, each taking up small percentages after that. But if we were to just combine into the built environment, mobility, and food production systems, those three alone consume around 90% of our total resources internationally. So this does let us identify what sectors would be important to target most of our efforts in circularity, in the bioeconomy, and in trying to improve sustainable resource uses. So then when we look at the waste that's produced from all of this resource, all of these resources that are extracted, again, unfortunately, construction comes in very badly here. And then that's only followed by the actual extraction process itself. So as you can see, particularly for the construction industry, we need to move away from that take, waste, and dispose of model. And this includes raw materials being continuously extracted and processed before being in landfill. And there are several definitions of what circularity means and what it means for specific sectors, but the commonality is that we want to eliminate out waste and pollution. We want to reuse and use products at their highest value and keep them within our system. And the important one for me as well is that we need to regenerate nature. And that's the one that's probably most often forgotten when we talk about circularity. So for me, circularity is like sustainability 2.0. We're not just talking about a little less energy here, subbing in renewables there, but instead we're aiming for a net positive impact. So next I'm showing what you might have seen is part of the Ellen MacArthur butterfly diagram, which is commonly used to describe what the circular economy is. On the left side of this diagram essentially is the bioeconomy side of things. So this is anything that deals with renewable biological resources from land and sea to produce things like food, energy, and materials, but also emphasizes recycling and using materials and reusing them again and again. And here we have the same example, but this time it's applied to the construction sector. And you'll see for construction for many years, and assumed here in this diagram as well, we just assume we're talking about timber all the time. And it's only more recently that anything outside of wood has been included in the discussion when it comes to the bioeconomy in construction. And we'll see here that when it comes to circularity, we want to stay within these inner loops as much as possible. And in these inner loops, it means we're taking products, we're taking materials, and we're minimally processing them as little as possible. And we want to maintain them in these inner loops with as little energy going into them, as little greenhouse gases being produced, as little new resources being used, before we start having to move to these outer loops where you can see there's more processing. The material looks less and less like its original form until it eventually goes into biomass energy recovery or back to fertilize the earth. So again, when we're talking about material choices and how we should prioritize our designs, this is a table that we came up with in the publication for Cost Action Circular B, where I just added a few examples from the construction sector to what each of these terms means. But we're supposed to stay more up in this green cycle when it comes to design. And what we really need to be doing is prioritizing refusing of changing materials, new resource extraction, rethinking how we design things by following the principles of a circular economy before we even start to look down here into reusing products, recycling, and the lowest on this table comes into recycling, which people often think is the pinnacle of sustainability. But really, when it comes to recycling, we're losing the inherent value that we originally created when we created a product in the first place. So this is where we move on to natural materials and how, for me, the further I got into circular economy and trying to apply circular principles to the construction industry, the further I came to natural materials as being the solution for this because of their natural ability to be renewable, and the fact that they can absorb CO2 during their growth phase. They seem kind of like a no-brainer for that reason. So natural systems are inherently circular in their behavior. They, the tree's leaves will fall to the ground and they'll nourish the soil, and then that'll feed the tree again. We don't need to put external energy into it. We don't need to transfer water from one location to another to feed it. And then when it dies, it returns to the earth, and a lot of that CO2 that it absorbs is released again. So we can look to nature and try and mimic this behavior to try and create balanced systems within whatever industry we're working in, and certainly for the industry that I'm working in, which is construction. So in Trinity, we've done a lot of work in bio-based construction. So we're working on an IP at the moment for 3D printed biocomposites, and we use a lot larger 3D printers that you would have seen in Pedro's presentation. We're using much wider nozzles because we're trying to form full wall systems out of fully bio-based biopolymers. We're also working on incorporating biochar into existing construction materials to try and make them more sustainable. So trying to introduce a carbon negative material into something to reduce its overall footprint. And we're also working on deconstructible timber-based connections and different connection types in construction so that we don't have that waste at the end of the building's life cycle. So when we're talking about bio-based, and this was mentioned before a little bit by Pedro, but we're talking really about anything that incorporates any amount of bio-based material. So it can be very minimal, the amount of fibers or say biochar that's in a concrete mix, and that will still be considered as being a bio-based material in construction. Whereas when we're talking about biofabricated, we're not really talking about processing something after it's been killed or cut. We're talking about something that is using biological organisms like bacteria or yeast or fungus, and that we can guide its growth into shapes that we want it to grow in. We can enhance its growth, we can feed it well, we can incubate it so that it does the things we want it to do, but it is doing the hard work on its own. So examples here in construction would be things like algae tiles, yeast biomass blocks, and mycelium panels, which is what we'll talk about today. So that brings us on to the mycelium project at Trinity and what we've been doing so far. And this is where we were approached by a furniture company who wanted to make their factories more sustainable. They wanted to do something circular with their sawdust waste. And with them, and supported by Enterprise Ireland, we've been working on developing mycelium panels using their sawdust to feed the fungal growth. So the basic steps involved in creating a mycelium panel is that you have some kind of natural substrate that's sterilized. You create a spawn inoculate from the fungus, which you can actually just purchase online, and then you can add the two together into a bag, incubate them together, and let it grow. And then you can start packing it into molds into whatever shape you need and heat treat it to stop that growth. So the company themselves did actually start messing around with some of this just in their offices. They had a few things growing and they weren't getting very far with it. So we began by just looking into how we could strengthen the material, because they wanted to potentially reuse what could be developed back into their own furniture. So, you know, the kind of backing boards within their furniture, or potentially use it as a spin out from that company to use cases in many different industries. So looking at what methods we could use to strengthen the material that we were developing, there is certainly hot pressing, cold pressing, the addition of fibers to enhance the bonds within the material, reinforcing with other particles, adding nutrients, making a better incubation system and more precise environment for them to grow, and also using binding agents. So in a sense, we were slightly tied in that they wanted to use their sawdust. So we were slightly tied on what materials we could use, but we certainly could create better incubation conditions as well. So we decided to focus on pressing and how we would press and when we would press as our main focus in trying to strengthen these panels. So the partners themselves were already sterilizing their sawdust on site and packing them into sterilization bags before sending them on to us. We just got the mycelium liquid culture, which was came in a liquid form, and we could inject the two together into a sterilized bag. And we would essentially pop that into an incubation chamber with enough space left in the bag for it to grow over the space of 2 weeks. And you can see there it began as the brown sawdust and ended up as this white mycelium spawn. So after that, we remixed it again with some sawdust and then compressed them into molds, and then covered that with PVC plastic sheeting, a bit like a cling film. And we placed that into an incubation chamber to allow it to grow again. And we had to make sure there were enough perforation holes in the PVC to allow for the air to come in. So we would have left that for a number of weeks, over 2 weeks. I think some of them needed 4, to enable it to colonize the substrate. And then lastly, we demolded them, oven dried them, and then went to pressing and testing. So just some lessons, and this is probably true for a lot of live systems if you plan on doing any research into these areas, is that people don't tend to like to share their equipment with live fungus or things that spore. Particularly, we have these high-tech climate chambers in Trinity, but we couldn't use them for these purposes, so we had to buy sort of a more like a, you know, more like something you'd put a snake in to keep them warm, with a little heater mat and a controlled temperature. So whatever we could find from the internet, we had to build that instead of using our high-tech system. The second lesson is that you have to allow for adequate airflow in these growing systems. They need oxygen, they need air to grow. And we found that initially we were just growing the white, we could see the white forming on one side, and then when we would demold, it was still brown sawdust on the other side, because that was originally covered by the mold that we had made. So we ended up then halfway through the process flipping our sample over and allowing the air to get to the other side a bit more. Our third lesson is that when we are pressing samples, when we press them really matters. We tried pressing them in the interim, so kind of halfway through their colonization. We tried pressing them at the end of colonization when it looked fully white, and we also tried hot pressing them, and there's quite a marked difference between the three. So we used standardized tests of the flexural test, which anyone who's in construction will know well, and a compression test. So these are 2 critical performance criteria when you're developing any kind of structural panel system. And we compared everything to our reference sample, which is not pressed. So you can see In orange there are compression tests, and in green there are flexural tests, which gives an indication of tensile behavior. In our reference sample, when we cold pressed after halfway of growth, and then when we cold pressed after full growth or full colonization, you can see there are big jumps between each of those phases. And then in the heat pressed samples after full colonization, there was a much bigger jump there at the end. So we always like to then go back and see what application can we use this in. So we looked at some benchmark materials that might be comparable, and we found that looking at our maximum compression strength and flexural strength that we're able to attain, they're closest to the high end of expanded polystyrene. So those hard insulation boards that you might find off the shelf, something similar to the hardest of those or the most rigid of those that you might identify. That's as close as we're getting. We're doing better than a lot of wood fiber boards. We're doing okay compared to chip boards in terms of density, but they're doing a lot better in their compressive strength and their flexural strength, because these really have these kind of very strong synthetic epoxies in them. So just some final notes on when you're developing any bio-based material or biofabricated material. Just be aware of the food first principle, and that is that we shouldn't be taking materials that could be used, or land use where it could be used or is used for the production of food for people or for animals. So generally, like in our case, we used a byproduct of the furniture factory and just took that sawdust as it was a waste material rather than taking a food. Be also mindful of the critical raw materials, and you can find a list of those if you just Google that term. It's a great industry to focus on if you want to replace some of this critical raw material with something that performs in the same way, but certainly don't include critical raw materials within any development that you have. Be aware also of safe and sustainable by design framework for chemicals and materials. So this is a good guide for how to develop your processes, your chemicals, how to treat them, and end of life, what you should do, and green chemistry whenever you're looking at your material practices. And then lastly, a just transition. So again, making sure that you're not taking land away from farmers, marginal landowners, etc., or any kind of minority groups that may be left behind, especially when we're making any major changes, like a changeover to a circular economy. And I'll leave it there. So thank you very much.